Alright, for number 4, this one a little bit different. Kind of like our class starter today, where we had to break that area for number 3 into 2 parts. We're going to have to do the volume the same way for right now. If we look at this, we're looking at the graph y equals square root of x, which we know is a sideways, half of a sideways parabola. Y equals 0, which would be the x-axis. X equals 1, and x equals 4. So we're looking at this region right here. And it tells us we're revolving around the y-axis, which tells us we're going to use a dy cut. But does this graph, this region, call for a dy cut? Not really, right? A dx cut will be better. But if we had a dx cut and rotate it around the y-axis, that's not going to create a washer. That's going to create a shell, which we don't know how to do yet. That's why we're going to do shells, because it's going to be easier than what we're about to do. What we need to do here is break it up into 2 parts. So we can actually look at this. If we're doing a dy cut, it's right minus left, right? So at first, we have the line minus the parabola. But then eventually, what happens? We have line minus line down here, right? So where does that change? At this intersection point, right? So if I go ahead and kind of draw a horizontal line right here, we break this up into 2 different regions. Right, we've got this like green region on the bottom, it's just a plain old rectangle. Yellow part, oops, on top. So we have 2 different regions. Basically, we have to find the volume of both of them and add them up. So for this first part, if we use a dy cut, rotate this around, we're going to get a washer. And for that part, our little radius is going from the axis of revolution to the closer function, which is y equals square root of x. But we're doing a dy cut. So this horizontal distance is equal to x, but we need to put it in terms of y. So this equation, we need to solve it for x. What would x equal? Y squared, right? So our radius here is equal to y squared. Our little radius is y squared. What's our big radius going to be? From the axis of revolution to the furthest part of the rectangle, what's that function? 4, right? So this big radius is always going to be 4. So sometimes that's nice, it works out as just a number. But if you look at this, like the big radius is always going to be 4, because this rectangle, the right side is always going to be on the line, x equals 4, right? The radius is the x value. Yeah.
Well, I thought we were all supposed to have it in terms of y.
Right.
Like 0.
So the radius is equal to the x value. Here, the x value changes. So we have to write down what it is in terms of y. But here, the x value doesn't change. It's always 4. This line, x equals 4, it's always 4. So it's constant. The radius is going to be constantly 4. Here, the radius is changing. The x value on the graph is always changing. So if we're looking at what happens with this region right here, as we rotate around the y-axis, we would have pi times the definite integral from our lowest y value to the biggest y value, which we need to figure out here in a second, of 4 squared, big radius squared, minus little radius squared, dy. So we need to figure out the lowest y value and highest y value. Well, this lowest y value occurs where these 2 graphs intersect. So that's the graph of x equals 1 and y equals square root of x. To figure out where they intersect, we can just substitute. Put 1 in for x. So y is square root of 1, which is 1. So this point right here is at 1, 1. So our lowest y value is 1. Our highest y value occurs right here where this curve intersects with x equals 4. So same thing, if we substitute 4 in there, we get y equals square root of 4, which is 2. So this is at the point 4, 2. So our highest y value is 2. We could also do that graphing on our calculator if we wanted to. But that is going to give us the area, I'm sorry, the volume, if we take this shape and rotate it around the y-axis. Now we need to add that to what happens when we take this rectangle and spin it around the y-axis. So we need to figure out the little radius and big radius for that one. Well, remember, little radius is always going to be the axis of revolution to the closest function. Well, the closest function here is x equals 1. If we look at a rectangle here, the left side of that rectangle is always going to be touching the line x equals 1. That means the little radius is always going to be 1. So our little radius is just 1. Our big radius goes from the axis of revolution to the furthest function, and that is x equals 4. The right side of the rectangle, no matter where we draw it or what rectangle we look at, it's always going to have a big radius of 4. So for this one, we're going to end up with 4 squared minus 1 squared dy. Our lowest y value for this would be 0. Highest y value is right here at 1, 1, so our highest y value is 1. Before we go ahead and evaluate this in our calculators, let's simplify it a little bit. Here we have pi times the definite integral from 1 to 2 of 16 minus y to the 4th dy plus pi times the definite integral from 0 to 1 of 16 minus 1, which is just 15 dy. So let's go ahead and put that in our calculator. We have math 9, we'll do this first one, 16 minus x to the 4th, comma x, comma 1, comma 2. So that's 9.8 pi for the first one. Plus, let's evaluate that other definite integral. We've got, actually, we don't really need a calculator for this one. Antiderivative of 15 dy would be 15y, and we're evaluating from 0 to 1. And we have pi out in front. So if we put the 1 in, we get 15, put 0 in, we get 0, so we end up with 15 pi. So our final answer here is 24.8 pi.